Hi guys, welcome back to my YouTube channel Code Ground, the battleground of coding. So let's solve today's daily coding challenge, that is trapping rainwater 2. Okay, so first let's understand the question. So I'm copying it. Yeah, so the question is given an m into an integer matrix height map representing the height of each unit cell in a 2D elevation map. Return the volume of water it can trap after raining. Okay, so let's first take a sample matrix and understand how this is going to work. So the sample matrix may be 2, 3, 2 and 2, 1, 2 and 2, 3, 1. Okay. So this is a sample matrix and the question is when it is rained on this matrix, how much water can it store? Okay. So firstly let's look at this cell, this 2. So can it store any water? No, because it is not having all the four boundaries. This the upper boundary and the left boundary is missing, so the water will spill out of the cell. So this cell cannot store any water. Same with this, same with this. So from this we get an insight that the cell can only store water if it is having all the four boundaries. So in our case, the cell which is having the only cell which is having all the four boundaries is this, the one. Okay. So, and let us trace out one more point. Let's suppose the height of the cell is x. So, all the four boundary cells should be having height greater than x. If any of the cell is having height less than or equal to x, then the water will spill out. So, this is one more insight. Okay. And how much amount of water can a cell store? The cell can store uh, the amount of water which is equal to the minimum of the all the four boundaries. Okay, here the cell value is 1. Okay, here 3, all the four boundaries are 3, 2, 3 and 2. What is the minimum? 2. So it can store 2 minus 1, which is 1 unit of water, because already the height of the cell is 1 and another 1 unit of water is getting stored, so it is 2, and the minimum of all the four boundaries is 2, so only 1 unit of water can be stored, that is 2 minus 1, that is min height of the boundaries minus height of the cell, amount of water can be stored. Okay, so what are we going to do in this process? The first thing we are going to do is mark step 1, mark all the corner and edge cells as visited. Okay, because they are not going to help us. And in the step 2, what are we going to do? We are going to use a priority queue to know the height of the minimum height of the walls, and then we are going to fill the water between the boundary, and then for that boundary we are going to again consider that as a cell. Okay, what does this mean? This means that after filling the water in a after filling the water in a cell, that cell can act as a boundary to the adjacent cell whose height is less than this height of this cell. Okay, understood. So this is what we are going to do in this solution. So let us see the code. Yeah. Okay. See, the code is quite simple. We are having a direction array uh, to traverse all the four directions. We have the lengths of we have the number of rows and the number of columns in the height map, and we are having a visited matrix which is initially false. Then we are having a priority queue. This cell is a class. Let me show you. This cell just contains the row, column, and the height. And this is the comparator to always sort the priority queue by the minimum height of the wall. And this is a function for the boundary conditions. Okay. Okay. So here in this part we are marking all the leftmost and the rightmost cells as visited. Okay, and in this loop we are marking all the topmost and the bottommost cells as visited because they are not going to help us, because if we try to store water, that will spill off because of no boundary. Okay, so this is the total amount of water we are going to store. Okay, and yeah, this this is the priority queue boundaries. Okay, we are going to perform this operation while until the priority key is not empty. Okay, we are going to step by step we are going to pop the topmost cell, and CR is the current row, CC is the current column, and min height is the current height. Okay, so for all the directions we are going to check the neighboring row and the neighboring column. Okay, uh, the uppermost, the upper, the lower, the right, and the left cells are going to be the neighboring cells. The neighboring row and the neighboring column we are going to check. And if it is in bounds, if it is not going out of bounds, and it is not visited, we are going to this is the neighboring height, the height of the neighboring cell. Okay, if the neighboring height is less than the minimum height, then we are going to uh, add the water in that cell. Okay, yeah, this is the condition to add the water, and then we are going to push the neighboring cell, uh, because that also became a boundary now. The height will be the maximum of neighboring height and the min height, and the neighboring row and the neighboring column. Okay, and visited of neighboring row comma neighboring column becomes true now. Okay, after this process we are going to return the total amount of water stored. Okay, so this is how we are going to solve this problem. Let's see if this works. Okay, yeah, this worked. Okay, let us submit. Great. Okay, so this is how we are going to solve this problem. And yeah, this is all for today. Please don't forget to like, share, and subscribe my channel. Yeah, and yeah, this is all I had to say. Thank you.